Good afternoon, ladies and gentlemen. I am Dr.Aula Alwattar from Chemistry Department in the University of Basra. I am pleased to join you today to talk about graphene. My talk is divided into 6 main sections. First, what is graphene? Then structure and properties, moving to application and production, graphene functionalization, and finally graphene dispersants. So that's what I am trying to communicate during the course of this talk. And then Dr. Kian is going to talk about graphene oxide, reduced graphene oxide, and all the characterization as he is a specialist in this area. Let's start with carbon, the essential element of life, and it's also the most abundant element on Earth. Single carbon atom consists of 6 protons, 6 or 7 neutrons, and 6 electrons. Carbon structure as graphite. You are sure familiar with graphite, a material used in pencil. But how about graphene? Graphite refers to a collection of carbon atoms or layers, and each layer of carbon atoms form honeycomb structure, which is called graphene. At the same time, in each 0.03 inches of graphite, there are about 3 million graphene layers. When you write layers of graphite, slide off the tip of the pencil and stick to the paper. Usually, many layers stack on top of each other, but once in a while you get a single layer of carbon atom that is graphene. Although scientists knew that graphene layers are the constituent of graphite for years, they weren't sure whether a monolayer of graphene could be isolated in nature until 2004. In 2004, two British physicists, Prof. Andrea and Prof. Constantine from the University of Manchester, they created graphene using very simple, very elegant method, using just graphite and Scottish tape. You can try this by yourself. So basically, they placed a graphite flake into the tape, fold it into two, and then cleave the flake in half. However, that isn't really a way for graphene mass production. They repeated this procedure a number of times and then studied the resulting fragments. In 2010, they won Nobel Prize for this discovery. They not only demonstrated the graphene can be isolated and stabilized in nature, they also carried out detailed studies of the properties of graphene. They found that graphene exhibited very interesting and unique properties that could be promising for a wide range of applications. Therefore, their research ignited great excitement throughout the world. Graphene has an extensive sp2 carbon network, as you can see here. This figure depicts the structure of graphene, a graphic which displays the in plane with the 3 sigma bonds which form 120 degrees, and the out of plane, a pi-electron cloud lies below and above the nodal XY axis. So this aromatic pi-electron system and structure are in control of the extraordinary thermal and electronic properties of mono, bi, and few layer graphene. Graphene is classified into 4 types: single layer graphene, bilayer graphene, few layer when the number of layers is less than 5, and multi-layer graphene when the number of layers is above 5, which is also called graphene nanoplates, as depicted in this figure. Now let's move to see what is the difference between graphene and some other carbon nanomaterials. As mentioned that these carbon atoms are bound within the plane by strong bonds into a honeycomb array composite comprised of 6-membered rings. By stacking of these layers on top of each other, the well-known 3-dimensional graphite crystal is formed. It is a basic building block for graphitic materials of all other dimensionalities. It can be wrapped up to 0D like fluorines, rolled into 2D like carbon nanotubes, or stacked into 3D like the graphite. So, what are the unique properties of graphene that make it so special? The aromatic bi-electron system and structure that have been mentioned in the previous slide are in control of the extraordinary thermal and electronic properties of mono, bi, and few layer graphene. Graphene has high carrier mobility, about 100 times higher than that of silicon, and an extraordinary electrical conductivity, which is about 60 times higher than that of a single-word carbon nanotube. Its electrical conductivity is stable over a variety of temperature, and this is necessary for reliable energy storage systems. One of the other things that make graphene so cool is that it's the thinnest materials you can imagine, 1 atom thick. This means this materials is mathematically two-dimensional, and you can still hold this single layer of atoms in your hand. Wow, doesn't this blow your mind? Graphene is incredibly stretchy. It can stretch as much as 25% of its length. This material also is really stiff. Actually, it's hardest materials people know about, harder than diamond, and that says a lot. In fact, nothing less than elephant balancing on a sharpened pencil will be able to pierce graphene, despite the 2D graphene can still be seen by the naked eye. So it's a combination of properties which makes it unique and so fascinating for so many scientists around the world. Almost every big university in the world has got a graphene research group. Arising from its unique structural and electronic properties, graphene features a number of other exceptional properties ranging from imperishable strength and elasticity to optical transparency and high surface area. The intriguing fact that it combines so many of these properties distinguishes graphene from other materials. This paves the grounds for a number of technical applications that range from energy storage to composite materials. As a result of these properties, it is reported as promising materials for various of application. Graphene, with its extraordinary strength, enhanced electron conductivity, lightness, and flexibility, is expected to play a major role in the development of next-generation solar cell, fuel cell, batteries that will have 10 times the electrical retention capacity of anything we have today. Photodetectors, light-emitting diode, solar cell, ultra-fast laser, and touchscreen. Owing to graphene's high surface area, theoretical surface area around 700 meters square per gram, it's an appealing compound and an auspicious candidate for applications in energy conversion, gas, and energy storage, supercapacitors, catalysis, as well as in micro and optoelectronics. Graphene has also generated great expectations in the biomedical field due to its extraordinary mechanical properties accompanied by biocompatibility, transparency, and electrical conductivity. More specifically, graphene offers mechanical compatibility, cell adhesion, and low toxicity properties for applications in scaffold production, sensing, and drug delivery. The latest application for graphene was a graphene-enhanced face mask. One key issue in the fight against COVID-19 is maintaining a supply of high-quality protective equipment, such as masks, gloves, and gowns for medical staff. Face masks, which can be re-sterilized and importantly reused. The mask offers enhanced antibacterial and antiviral protection for its wearer use. Of an advanced graphene material provides a robust strength whilst providing thermal cooling properties. In terms of the biomedical application, as we mentioned, such bioimaging, sensing, delivery, graphene-based nanomaterials can be either biocompatible or toxic to biological cells. The response of living cells to these nanomaterials depend greatly on their layer number, lateral size, purity, dose, surface chemistry, and hydrophilicity. The surface chemistries of graphene nanomaterials greatly because of different strategies adopted for their synthesis and the availability of different molecules or polymer for surface functionalization. Despite its apparent properties, the application of graphene on an industrial scale in real-world applications struggles from difficulties in production, small scale in production of either single or few-layered small sheets, which is considered a major downside. Moving to graphene production. In order for the potential applications graphene to be applied in reality, there has been a tremendous effort to find methods that meet the need for large-scale production of defect-free graphene in reproducible manner. High-quality graphene at low cost and tailoring graphene to a suitable form are amongst the greatest challenges being faced in this field today. Bottom-up and top-down are the main two methods of the synthesis of graphene. Bottom-up. In the bottom-up approach, which relies on atom-by-atom growth, chemical vapor deposition, CVD, has been applied to solve the problem of the low yield of graphene's production in micromechanical cleavage. The most common method of this approach is illustrated in this figure, which illustrates the key process by using carbon segregation, metal carbon segregation, and chemical synthesis. Furthermore, the chemical vapor deposition. The organic synthesis of large fused aromatic system is a process for graphene production, which involves the synthesis of a molecular nanographene, including graphene quantum dots and nanographene ribbons of molecular. The main advantages of this method are defined chemical structure, processability, and the scalability of produced graphene. However, this method has its limitation and is generally less applicable as the extended polyaromatic hydrocarbons become increasingly difficult to handle. The precise characterizations of these structures become difficult, and the probability of side reaction, which cause defect in the produced molecular graphene, increase with size. These limitations are considered to be the main challenges that are associated with this method. This figure shows example of synthesized molecular graphene models such as hexabenzocoronene, graphene quantum, and graphene nanoribbons. All this via the Scholl reaction and using alteration of dendritic polyphenolines as starting materials and FeCl3 as an oxidizing agent. And the red bond here is just to show you like a new formed bond during the course of this reaction. During my PhD, I investigated the use of Scholl type reaction on 4,10-disubstituted glycine derivatives, proceeds via variegated and unexpected oxidation coupling pathways. These observations serve as a cautionary note when attempting to employ the Scholl reaction in targeted oriented material synthesis. Moving to the second approach, this is top-down, which is divided into two categories: dry exfoliation, which involves the micromechanical cleavage using an adhesive tape, and liquid phase exfoliation LPE, which depends on the exfoliation of natural graphite into the 2D graphene sheets. This can be achieved under a variety of environments and can give limited film sizes, but may be advantageous in terms of cost. LPE can be subdivided into diverse types such as solvothermal assisted, electrochemical, high shear mixing, ultrasound induced LPE, wet ball milling of graphite, graphite intercalation, as shown in this figure. Some of the top-down methods to synthesize graphene, which illustrate the key process. All these processes have been reported to take place in either organic or aqueous solvent, as well as in ionic liquid. All the above-mentioned methods produce different qualities of graphene with varying flake thicknesses, size, and grain boundaries. Basically, different properties for different graphene materials are afforded by these types for various potential applications. Mostly, the use of water as a solvent in LPE is challenging because of the inherent hydrophobic nature of graphene, which makes it difficult to disperse and stabilize in water. This video shows you this. So here we have some graphite on the left and some graphene on the right. When there is mixed with water, you see the graphite start to disperse freely top of the graphene, and this is due to the hydrophobicity difference between them. This leads me to my second point. Now, you might wonder and ask, if graphene is an amazing material itself, why there is a need for graphene derivatives? Well, that's okay. I will tell you why. Some graphene properties limit its applications, such as dispersibility in water and zero-gap semiconductor, a problem for implementation into semiconducting device, and the tendency to aggregate, as I've mentioned in the earlier slides. So 10 layers of graphene behave like graphite. However, this can be tuned by functionalization. Some of the problems associated with solution processing of graphene include the reaggregation and restacking of graphene layers in solution, forming continuous films of graphene. This occurs as a result of the strong interlayer van der Waals forces with a view to reduce surface free energy. Alteration of the graphene surface in order to overcome this issue can be achieved by either functionalization covalently, which is not favorable because it disturbs the aromatic system within the basal planes, influencing the conductivity of graphene, or by stabilization non-covalently, which means dispersion of graphene in particular solvents as schematized in this figure. So basically, this figure shows you the dispersion of graphite to produce graphene in the presence of either solvent or surfactant. As you see here, the surfactant sits between the graphene layer and prevents this layer from the restacking and reaggregation. Liquid phase exfoliation depends on the exfoliation of a natural graphite in organic or aqueous solvent into the 2D graphene sheets by means of ultrasound waves, which consist of refraction and compression cycles where the cavitation takes place. This method has been used for scalable graphene production. Typically, hundreds of milliliters of graphene dispersion can be produced by ultrasonic exfoliation, with lateral size of a few layers stick ranging between 50 nanometer to 2 micrometer, depending on the starting materials. And generally, its process comprises of three steps: dispersion of bulk materials in a solvent, exfoliation, and purification. This method had the potential to be an integral part of graphene production, which can be achieved under a variety of environments and can give limited film sizes, but may be advantageous in terms of cost and mass production of graphene dispersion compared to bottom-up methods involving complex synthetic procedure. In LPE, the use of solvents such as NMP and DMF along with orthodichlorobenzene are commonplace, but their toxicity and high boiling points poses severe limitation in their use on a large scale. In order to avoid these problems, the search for more benign solvents such as water has been the subject of much research, especially for the green chemistry viewpoint. The use of water as solvent in LPE is challenging because of the propensity of graphene to self-aggregate and the quest for efficient stabilizer which ameliorates such effect has been an active area of research. This figures representative stabilizer use in graphene exfoliation. And as you see here, so this stabilizer it like works as surfactant, so it has like a hydrophobic part and hydrophilic parts. Pyrene 1-sulfonate is one of the most frequently reported small molecule stabilizer in the literature. In my group, we built a modular structure of a molecule designed for non-covalent functionalization of graphene. A preliminary study, the stabilizing ability of commercial available PSA and pyrene butyl sulfonic acid salts, as you see here, PBSA, was compared. PBSA was synthesized in 3 steps as shown in this scheme. PSA is effective at producing aqueous graphene dispersion of up to 0.7 milligram per milliliters. But its structure is likely to be far from ideal for this function. Based on a study in the literature by Green Group, they observed that pyrene derivatives with sulfonyl group yielded higher graphene concentrations than their carboxylic acid analogs, and also that one pyrene butyric acid outperformed one pyrene carboxylic acid. Therefore, it was hypothesized that installation of an alkyl chain between the adsorption platform pyrene and the functional group, which is the sulfonate, would improve the efficacy between the hydrophobic pyrene and hydrophilic salt residue transitions the original structure towards that of the traditional surfactant. Our result indicated that the introduction of conformationally mobile spacer, in this case, the N-butyl group between a planar aromatic residue, and this is for pi-pi interaction with the graphene or RGO surface, and a polar head group, which is the sulfonate. So basically the sulfonate residue interaction with the solvent, and it is water in this case, generated a molecule, PBSA, that was more effective as a stabilizer than parent compound. Today, there are a few systematic studies concerning the design of graphene dispersion stabilizing agents, and following the encouraging results from our PSA and PPSA, a modular approach was adopted again. If you can see here, is the same as the modular before. And this is to gain, in order to gain and generate a small library of new compounds for graphene dispersants. The main focus of my research was to identify new graphene stabilizing agents for the exfoliation of graphene and RGO with the aim of designing and synthesizing a new asymmetrical substituted of various aromatic cores asymmetrically substituted with the amphilyl group SO3Na. Within the library, the nature of the adsorption platform, which is here the aromatic footprints and the spacer units, was modified in a systematic fashion. Stronger adsorption into graphene could increase the dispersion stability, which has the potential to improve concentration as well as the lifetime of the resultant aqueous graphene dispersions. Therefore, the substrates were designed to incorporate different aromatic motifs, including triphenylene, pyrene, and pyrrolene, to investigate their influence on dispersion stability. So I hope that you are a little clearer on how we can produce graphene, why graphene dispersion stabilizing agents are necessary to produce stable graphene dispersions, and how the layers number, lateral flake size, purity affect the potential application of graphene. That's me at the end of my talk, so I will now hand over to Dr. Kian. I would be happy to answer any question you may have at the end of this session.